with what I want to do next. I really do need to preface my discussion with a couple of small things from your past. Number one, you learned from trigonometry that if you have a circle with radius r, its central angle is measured theta in radians, subtended by an arc of length s, there's a relationship among those three quantities. If you don't recall how, it's a piece of cake. I just think looking at the pretty picture, it's natural to assume that this amount of rotation divided by the amount of rotation from one full rotation should be the same as the ratio of the length of the arc subtended by that angle to the circumference, which corresponds to the arc for that angle. But the circumference of any circle is just this. And when I multiply both sides by that, this is what I get. So clearly that relationship is true. So keep that in mind. The length of an arc subtending an angle of measured theta radians for a circle whose radius r is just a product of the radius and the measure of the angle. Something else you read in the textbook, I have not mentioned it, but you read it in the textbook, what I call the squeeze theorem. Now, the squeeze theorem says this. Got three functions f, g, and h that have this relationship, at least over some interval that's open and contains a. So here's f. Here's g. And here's h. And so if it's the case that their outputs have this relationship, and it's also the case that the limit of the outer two ones, as x goes to a, is the same thing, just namely L, then it has to be the case that that one function g sandwiched or squeezed in between these two necessarily has the same limit. So having said all of that, let's see if we can tackle this bigger issue. I want to know what the derivative of the sine function is. Now, I guess since I don't know anything about derivatives of trig functions, I have no choice. I have to go back to my limit of a difference quotient. And let me just play with this for a few moments. We do have handy in our back pocket, in addition, angle identity for the sine function. Now, next on my list, let me go and associate the first and third terms in the numerator. And merely this single term, middle term all by itself. Split it up into two different fractions. Take the limit. Continue to break up further with my limit laws. And check out how this didn't help that much, at least not yet. You've added that limit right there, as well as this limit over here gives me my indeterminate form 0 over 0. I need to get out of the trap. So here I am, getting out of that trap. That's a portion of the unit circle, the portion of the unit circle in the first quadrant. Here is an arbitrary angle in standard position, whose terminal side is in the first quadrant, whose measures t radians. Now, this is the unit circle, so clearly the length of the arc is just t. Now, let me put a few points in. Dropping vertically down. So would you not agree that if I had a point unit circle right there, its coordinates would be the cosine of t and the sine of t? But the sine of t being the y coordinate means this length right here is the sine of t. Now, if I label this point B right here, would you not agree that what I'm drawing right now, the line segment connecting A to B, is a hypotenuse of a right triangle? And so the length of one of its legs is going to be less than the length of the hypotenuse. So this would be strictly less than the length of the line segment connecting A to B. Now, I have to confess, everybody, I don't want to be this restrictive because technically speaking, what if D had to measure 0 radians? That being the case, I think both of these have the same value. They're both 0. So if you don't mind, I'll include equality. Although it doesn't really make sense with a triangle, I'm just saying T itself could be 0. Now, take a peek at how this is the length of a quarter of a circle. And therefore, the length of the arc, which is going to be the measure of the arc from A to B, is necessarily larger than. Unless, of course, I'm one of those extreme cases where T is equal to 0, equality is included. But as we discussed, to measure the arc is just T. So look what I have on the board from beginning to end. So I have that the sine of T is less than or equal to T, or shall we say the sine of T over T is less than or equal to 1. Now let me continue playing with my pretty picture. Let's take a peek at the tangent line to my circle at the point A. Let's take a peek at a vertical tangent line to my unit circle at the point B. And let's say they intersect at point C. Now, because this is a tangent line and that's a tangent line, so this is a tangent line and this one is, that point C is necessarily external to the circle. So I think clearly to measure the arc from A to B, am I getting too sloppy? I said to measure the arc from A to B, which by the way is nothing more than T, has got to be strictly less than the sum of the lengths AC and BC. But again, that extreme case can apply. Now take a peek at how, if I extend the radius from the origin to A beyond the circle, that's a normal line to the circle. So it's necessarily perpendicular to the tangent line. And so now take a peek at the triangle connecting the vertices A to D to C. So A to D to C. That's a right triangle. And DC is a hypotenuse. AC is not, it's just a leg. So this AC is going to be less than or equal to DC. But DC plus BC is nothing more than BD. But if you think about it, that length is 1. And so the ratio BD to 1 is just a tangent of T because that's opposite over adjacent. Now from beginning to end, notice what this really says. It says that T is less than or equal to tangent of T. That implies this. That implies this. Now, if you put both these together, notice what it really says. It says this ratio is squeezed or sandwiched between this extreme and this extreme. But since the limit of these out ones as t goes to 0 is equal to 1, then it's got to be the case that the limit as t goes to 0 of this ratio is also going to have to be 1 by the squeeze theorem. That being the case, things are looking pretty good down here. Don't know what that is yet. I know that this is 1. Now, for me to handle that limit, cosine of h minus 1 over h. Let's multiply the top and bottom by the conjugate of the numerator. So you ready? We already proved that goes to 1. Clearly, this goes to 1 half. That goes to 0. And so the entire product goes to 0. What that really means is this. That when it comes to derivative sine of x, it's this times 0 plus cosine of x times 1, meaning we have just derived that the derivative of the sine of x is the cosine of x. Pretty slick stuff if you think about it, because we already have one intimate relationship between the two functions. That's the Pythagorean identity, at least the first one. Now we have a second intimate relationship between them in terms of their derivatives, at least in one direction.